My name is Daniel Ayer, and this is my BasketTube AI game analyzer for DS681 here at NJIT. The point of this is to build an AI game analyzer that can extract and verify player actions from the basketball game video using a visual vision language model. This, I will say, is a proof of concept video. This non-near production requires many refactors. It is specifically only on this one game video, and ideally we would take what we've learned here and build a larger pipeline that could take in many videos, analyze them all, and come up with a better, stronger model. But since we only have one game to analyze, let's get into that. Here's our game, Warriors versus Lakers. Insta Classic from 2021. And what we want in the first task is to use the commentary in order to generate a VLM or to generate, identify semantic events within the video. So here we want to be able to ask, analyze the player that scored the most in this game, and then it should give some sort of response. So what we have done, or what I have done in this project, is use Claude Sonnet as the LLM trainer. So Claude Sonnet was fed with the LLM prompts for various inputs. Those were then fed back and saved as tokens, and then used to train our VLM, which is using Polygemma. I always say Polygemma. I don't know how to describe it, but Polygemma 3B LoRa, I think, is what we're using there. Anyway, in this case, what we're doing is we're taking the audio, and we're taking the audio of the video, right? So it's a game with audio commentary, and we're using Whisper to create a transcript of that. Once we've done that, then we're going to go through these, just analyzing descriptions, segment lengths, distributions. We have a clip and projection layer architecture. So what we're actually doing is, in a standard VLM, what we're trying to do is have an image linked with text. So you have an LLM, a large language model's embedding space is designed for text embeddings. But we can actually take video, and through a really cool perception filter, we can try to project those video embeddings into the text space. And the idea is that in that embed space, now it's all technically text embeds, but we're trying to align the video or the visual embeds to get as close to those text words. So if I had a picture of an apple, I would say apple. And then ideally within that embed space, the text embed apple would be very close to an analogous visual embed, which is really text, but into it would be close to that. Imagine putting on glasses, right? So if I have blurry vision, that's because the world is giving me a signal that my eyes cannot interpret. That input is blurry to me. With glasses, it aligns it to what my eyes can process, and then I can see clearly. To someone else putting on those glasses, they would not be able to see clearly. It would be blurry because it's misaligned for what they need, and that's what we're doing here. So instead of doing a single image embed, what I thought is maybe we could do a series of image embeds, concat those together and feed those in. So instead of a single frame being associated with the LLM text embed space, we would have several frames. 3 in this case is what we're going to do. We have a frame start and a frame mid. Time start, middle, there's an end in here that didn't get captured. So we have a frozen clip embed. And we actually, with my laptop, I could not concatenate these images together and feed them through. There's dimension aspects, but even with resizing, even with readjusting, even if we train it up from the ground, which I tried to do, my laptop is just not powerful enough. So what I did was, instead, I walked through each frame embed individually. Those are embedded in clip. And then I took those embeds and concatenated those together, hoping that that would give us a richer sort of timeline to examine up to the commentary. The commentary, again, is based on the events that have led up to what these people are saying. So future events, it doesn't make any sense to include those into this sort of context window. that we're making. So what we're actually doing is grabbing 3 frames per subtitle segment. And what that is doing is the end is the last image associated with that statement. So if you were to watch the video and had the subtitles running, when that subtitle disappears, that frame, that is our beginning frame. And then we march backwards from that in time in sweeps of 3 seconds, 5 seconds, and 10 and 20. And what happens is we can't actually grab all of those frames. In each case, for this project, we are grabbing 3 images, but in a broader or tighter window, or leading back from when the subtitles were or the comment was made. And hopefully that would give us some feed, some information that would lead up to that. That was the idea. Let's see. Now we're using cosine similarity in order to determine which things are analogous in our query. So if I say something like, show me Stephen Curry making 3-pointers, it's going to use the cosine similarity within that embed space around those text tokens, looking for visual embeds that it can get at. And again, they're not truly visual. They've been warped and distended into this space. But so as we go through here, we can see here is our cosine embedding loss by context window and the retrieval similarity by context window. Here, 3 seconds actually outperforms or equally performs, but I chose 5 just because it made the videos a little bit more punchy. I mean, a 3-second video isn't a lot of evidence. So there's a balance between how much video I want to play back. Maybe I could just extend that a little bit. Again, there's a lot of stuff that I learned here. I only had 2 weeks, and I would really polish this up a lot more at a later date. Okay, so the live demo here, we will have a direct response, a summary, evidence, and disclaimer as per the assignment. And then let's just see that in practice. Again, with my laptop setup, I have to run this BNB CUDA version 128, Python, my basket, and this player performance VLM is my VLM. So let's fire that up. It's going to go through. It's going to load stuff. Okay, now I can run a query. So what if I did a query for something like free throws? So it's going to go through now. It's going to look into that embed space for the space around where free throws would be. And then it's going to grab images that would sort of give evidence for that. That should show these events. And then it's going to generate a playlist because chunking out the actual video was just taking up too much disk space, and it was much easier to just have it make a playlist. The playlist is going to be cut together of shots that in this case would be free throws. That is the goal. Now, I will say that this works really well in some cases and not really well with other queries. And it's, I think, because this is all based on commentary. If no one commented on it, then unfortunately this system cannot identify it. It's very different than the original approach that I was hoping to use by tracking the basketball's motion in order to identify semantic events and then reach back into the commentary to find the commentary associated with that. Different structure I'll talk about soon. So here we can see if I go back up, we have free throws. Here's our direct response. Foul has been called on the play. So this is a description of what's going on. This is generated by our VLM. The summary, VLM. The evidence with timestamps. These are all the same timestamps. And then it says the commentary is here, and the VLM is saying, hey, the visual evidence is that the scoreboard says it. This is what's going on. Here's what's going on. And then a disclaimer is based on 3 frames from 1 commentary segment, and so on. Let's see. Then it's going to go through, and for every little piece here, he puts himself in position to take the hit. This is the commentary that it has identified and is responding to with the evidence. If we go down a little bit, here's another timestamp, right? With more direct summaries and such. But the real meat and potatoes of this is not this text. Maybe it's the text. Maybe you like the text, but what I prefer is this part. So I'm going to go here to videos. And we can see here, this is an old development where I have a development result where here are the playlists and here's the context windows, 3 seconds, 5 seconds, 10 seconds. If you go in here, these are all different, let's see, context window. Curry hits a three-pointer. So that would be a video of the 3 seconds, 5 second, 10-second window. This is the old system developing sort of as a demo what we could see. This is our current result that we just ran, picking a 5 second context window. And oh, these are all older queries that I forgot to clear out. But what we did was free throws. So let's take a look at free throws. Now that matches the text that we had, right? So these are all. So these actually seem to be more associated with fouls, and when I search for fouls, it's very different. So I guess this is all like the results leading up to it. I don't know. It's very opaque what we're talking about. If I actually run fouls, I don't want to run the old queries again, except to demonstrate this, that if I were to run the query again, let's go up, and the query was free throws. So if I type free throws again, boom, it's done. So this actually caches all of our results. I like this part of the system very much because initially we were using API calls, very expensive, and I didn't want to waste all of that. So when we were grabbing down our training calls for the VLM, we cached those, and I said, hey, let's just stick out with that. So here's our query cache. And you can see within here that analyze the player that scored the most in the game is a previous query that I made, and that it has these results here, so it can just give it back to us really fast. Oh, it even has similarity scores, right? And the frames and the subtitle or the audio that was associated with it, and when in the game. Stephen Curry three-pointer, right? So all of these, if I were to do Stephen Curry three-pointer, you will see, boom, it just gave me what has been cached from the previous, right? And it says here, where it says a three-pointer cache response. So it's giving us a cache response, telling us that. So we could go in and clear the cache if we had to. And then it says, here, Steph Curry attempts a step back three-pointer, right? So this is our direct, with the game tied at 57-56, and the Lakers holding. So here's the summary of what's happening. And here's evidence backing up that this is actually what we care about. Now, more compelling, I think, as a proof of concept is that I go into here and in our 5 second context window, Steph Curry three-pointer. Let's see what we get with that. Curry, three-pointer. Right? He doesn't make it, but he does it. And what's interesting is when I search for a foul, that foul does not come up. It's so crazy. But here's Curry. Here's Curry, passes and shoots. That's a three-point shot, not by Curry, but within this context window next to Curry. Right? There's a three-point shot right there. So we can see that this is actually really good at identifying three-pointers and potentially the player that is associated with it. Curry with a pass and pass back. Now Curry with a three-pointer, right? So it just keeps going. This is our playlist running. This is all the same video. It's not being chunked out. It's just pulling these little segments. Let's watch this last one. Oh, no, we can't because of that context window. So maybe we could grab larger ones. When I ran fouls, again, this is the consequence of a foul. So here's LeBron sitting there and he's fouled, and this entire stream is just the consequence of the foul, but not the actual fouls. When I ask for analyze the player that scored the most, it gave this of LeBron James. I assume he's the one that scored the most. The trick here is that we only have the audio commentary on which to train in this task. Okay. So now we'll go into the second task. And the second task, let's go back to our project. Live demo, we did that. Okay, let's go down. Okay, and here's our local VLM, Polygemma QLoRa. Okay, we got our training epochs and loss. Again, we could get much better results from this if we had more data to train upon. You can see the loss drop off. Okay, so verify the player actions from the video, detection and pipeline. So I don't want to go too much into the architecture, but what I did was the idea for this part of it was actually to do to track the events by the ball. So the ball in all of these games should encode everything about the game, the state of the game, or rather its trajectory, right? Baseball, basketball, we're tracking a ball. The point is to get the ball into a goal. So this is the first sweep was let's only analyze those cells that have the ball. So this is a detection that we use with RFD-ETR. Now we did build our rich information stepwise. So our data is built stepwise here. And you can see here that there are detections. There's data frames. This is a data frame of all the balls, of the detections. The data frames are really the workhorses here. You can see I took vectors. We'll talk about bucketing the vectors later. But all of these, as we go, allows us to pull back, call this data back up. These are sort of our databases. So we don't have to rerun the same thing over and over and over. You can see that here, ball detection, motion vectors, player detections on the ball. Okay, so this was our core thesis that we could track the ball's motion, and that would be it. And that was great. That worked pretty well, except I hit a brick wall and then it fell apart. And the reason is it's just too sparse. This video does not have enough information about semantic events for us to do a unsupervised or semi-supervised learning, which is really what I was going for with like a TCC style. But the problem is, for instance, if someone shoots the ball, we're humans. We don't care about the big shot. We want to zoom in on the ball, which means we're tracking the ball, and relative to each frame, the ball appears stationary. The background is what's moving. So in future, we would add some functionality to maybe detect parallax or something like that and get really the actual motion of the ball. And I actually think that we could do it that way from publicly available videos, or we could have a stationary camera that is taking in the entire game, still able to track the ball, and is able to chunk it out from there. But let's look at what we did and how far we got, because this was really my innovation, and I'm pretty proud of it. So what we did was get the data, the motion vectors as best as we could from what we had, and we got something like this. Each one of these is a vector, a motion vector. So this is one event passing the ball very far. The red ones, this is a logarithmic scale. The gray ones you can't see, those are very small. Those are just noise. We got rid of those, like dribbling and whatnot. Long, log, medium are these blue ones in here, and I believe that these are the important play determinants. And the log short, remember these are all log based, are these big long ones. And actually, if you zoom in around these little areas, right, every vertice, we can see, let's do this vertices, we can see that at all these vertices, we have these clusters of blue motion, of smaller motions. So I really think that there is something here. However, this is just too noisy. The data was just way too noisy. We unrolled them, so what's happening here is you can see the balls are allowed, or the vectors are allowed to feed back on themselves. It's sort of directional, like a map of where it is, sort of scaled a little bit. These are cumulative values, so it's not exactly a one-to-one mapping, but it does give us an idea of where to look. That was the idea. Maybe we could get something that semantically pointed to the events that we are hoping to get. Now I thought, well, what if we could plot them without that backtracking allowed? So each thing along here, let's see, boop, we can see these events. So each of these ups, up and downs, these are all individual vectors. And I really think that in here, in this data, perhaps there is a gap here that we could identify as, I don't know, as having a dribble, because this would be up and down, up and down, up and down, right? And we could see something like that. However, it was insufficient to our task. Let me just reset this real quick. But I really am excited about this as a potential. Now, if we go down here, we can visualize this is very noisy. I'm not sure if this is really helpful. These were all very helpful in attempting to find signal in noise, and I think I ruled these as noise. Using the ball centroids was not very good. The L2 distance spikes to detect event boundaries, same thing. It's very noisy. This is all trying to do a semi-supervised or unsupervised. I even tried to identify the different vectors, do this DTW UMAP motion sequence embedding to see if I would get good clusters, but you can see they're not really well clustered. They're all spread out, which maybe makes sense. The idea here was maybe to detect dribbles and things like that. Let's see, normalized motion magnitude again. This is, you can see there's a big spike of events here. Okay, play by chunk. Yeah, okay, and this was our attempt to link events to the players. Um, and what we managed to do is get, I know I'm running out of time, I'm really sorry about that, but so we have here that Stephen Curry enters the game for somebody. That's twice? No, action type break. That's a type of action label. So we're trying to say like all of these are the same type of event. 3-point jump shot, 3-point, 3-point, maybe it's a 3-point, 2-pointer. These all look like shots. Event 2 is a shot, I would say. So the idea was not to label them, but to try to get it to identify these events on its own. We would apply our labels after the fact. So we also wanted to break this out so you could do it by quarter, and which quarter did things occur. And so you can see here that we were able to do anchor mapping. It was really hard because the video itself is continuous. We did find a source of labels from another, where is it? From another site where they've already have a lot more annotation. Play-by-play frames, I think, was pulled from there. And we were able to use that site and its labels. These are all labels provided by the site in order to try to identify semantic events. Right, we were able to have the system learn the team. This really didn't work. Their colors are inverted from each other. Yellow lettering on purple shirt, purple lettering on yellow shirt proved way too hard, like surprisingly hard. But you can see here that there are actions here of a certain type. It tells you when did they occur. These are sequential frames, 30 frames per second. So this is the frame we think it occurs. Okay, so now that we have all of these anchors, so essentially this flow is we're going in sweeps, and every sweep populates a new data frame or a new something. We're taking that previous step, and instead of doing it in a real-time way, this is an offline analysis. Let's go down because we wanted to see here. Okay, so here it's a little bit hard to see, but there's a video that it produces. We were able to track the ball. Let's pull up that video real quick. We were able to visualize these tracks. You can see here. Again, it's really difficult to identify the players. This guy's a Warrior. He's identified as a Laker, right? And he's going to take a shot. Boom, right? So we're able to identify these players. And with this information and more time, along with what we have up here, with our event types, we could really bring this home. Unfortunately, like I said, this entire project, 2 weeks in, and now I've just hit a wall of work. I really hope that that you found this interesting, that you have questions. I have a lot of questions, and that I will probably do more of this over the summer. And I appreciate your time, and have a good one.